Hello guys, my name is Amay and I am a student of IIT Bombay from the Mechanical Engineering Department. So today we will be continuing with our topic of integral calculus, and today we'll study double and triple integrals. So uh, double integrals and triple integrals are basically used to mainly calculate areas and volumes. They are used in several branches of engineering as well as mathematics for calculation of areas and volumes of complex shapes. There are different techniques to solve double and triple integrals, including various uh, substitutions, which make the manual integration a lot easier. Some of which we'll be studying from the next lecture onwards. So, uh, for double integrals, let me define at the elementary regions, which are basically uh, different types of regions in which we can integrate our function and obtain a result. Obviously, the functions that you get in real life are way more complex, but to start, we define two types of elementary regions, type 1 and type 2. Um, why is it possible to integrate these functions doubly? Because we define a standard boundary called del D as the boundary of domain D. For elementary regions, this del D by convention is defined to be a set of content 0. So that any function defined on this domain is Riemann integrable, because if you remember in the second lecture we had studied this point that for uh, if the set of the interval or domain on which we are calculating the integral is a set of content 0, then the function is Riemann integrable. So the first type of region which we define here is this, where we have taken two intervals of x and a, and the upper and lower values of y are functions of x, pure functions of x. So you can see that it is easy to calculate the area of the function in this domain as an iterated integral, y going from h1x to h2x. So first we solve this y integral, and then we solve the x integral going from a to b. In type 2, we have taken a similar shape, but we have taken it along the y-axis. So the upper and lower limits are defined in terms of y, while the right and left limits are pure functions of y. Again, to find the area of this domain, we need to solve these two iterated integrals. A third type of region can be defined, which is what you will mostly be asked to find in exam questions, which is a bounded region, which is neither type 1 nor type 2. And two examples I have taken over here, which is one is annulus and the other is a star. So the goal in these type of questions is to break up the type 3 region into type 1 and type 2 regions, which can be easily integrated. So let us take this annulus. Annulus is basically a ring which is hollow on the inside. So it has an inner radius, here it is S, and an outer radius R. So the inner function of y, that is this entire thing, can be taken to be h1 of x, while this function can be taken to be h2 of x. We can see clearly that in this region, x going from minus r to minus x and x going from s to r, the function has taken a value 0. And in this region, it is a hemisphere, hemicircle. So here it is root s square minus x square. Why we can say this? Because let us take some point on this function here. So the value at that point will be y, that is the function value, which can also be written as h1. And this point is located at a distance x from the origin. So this is x and this is h1. And the length of the radius is s for the inner circle. So using Pythagoras theorem, we can say that x square plus h1 square is s square. So h1 can be written as root s square minus x square. Similarly, for h2 we can define by taking a point here somewhere on this semicircle. So this distance is x, this value is h2, and the radius is r. So by Pythagoras theorem, h2 can be written as root r square minus x square. Now we define the domain in this case. Uh, so here we can see that since this region is not type 1 or type 2, we need to break it up into different regions. We can see that this region is clearly a type 1 region. Remember that this was type 1 where the endpoints are constants in x, and this region is type 2, so the endpoints are constants in y. So for this domain we need to define it as follows: y is between minus r and r, and x is between minus r and y is between h1 and h2, while domain 2 is the domain in these two regions. So we need to take the boundaries k1 and k2 as we saw in this. So k1 is s, which is this vertical line here, and k2, for k2 we need to take some point on the circle, and we can see that k2 will be root r square minus y square, because if we take the distance of this point from the center line, this distance will be y, and this radius from the center is r. So the value of the function k2 is root r square minus y square. So we can define domain 2 like this, and we can integrate this function in both type 1 region and type 2 region, and then take a sum of those two integrals to get the entire area under this curve. Similarly, for a star shape region, we can divide it into 5 parts. This region is type 1, while these 4 regions are type 2, and just apply the procedure that was explained. This will be slightly lengthy, but it is the same procedure and you will get an answer. Another thing to note is symmetry in integrals. Several of the questions that may be asked in exams may contain symmetry. So be careful to watch out for this, and if symmetry is present, your problem has become very easy and you don't have to manually integrate the entire function. So sometimes you may get questions like this where the integrand is somewhat complex and it will take some time to evaluate the double integral, but you just need to observe the domain which you are given. Here the domain is given to be this, which is a circle with center 0 and radius 1, which is symmetric about both the x and y axis. Here we can see that this function 2 sine x is an odd function. So imagine if you had a circle like this, then this function would be somewhat like this. Since it is an odd function, it is anti-symmetric about the x-axis, while y cube is anti-symmetric about the y-axis. So you can see that since both these functions are odd functions and the domain is entirely symmetric, we can conclude that the integrals of these two functions will be 0. Because think about it, if the since this function is anti-symmetric, whatever area of this region above the x-axis taken with positive sign will be the same as the region below the x-axis taken with a negative sign. So the net area contribution due to both these parts will be 0, which means that this integral is only equal to 5 into dx dy. You can see how easy it has become now. So 5 is a constant, so it will come out, and dx dy is the area of this disk, which we know is pi r square. So the value of this function is 5 pi. Similarly, if we have a function like this, we can see that this is an even function and the domain is a sphere with center 0 and radius 2. So since this this part is an even function, and if multiplied by x it becomes odd. So again, with respect to x-axis, whatever part is above the x-axis and below the x-axis will get cut, because about 0 both these parts will be of opposite signs. Now let us define triple integrals. Like I said earlier, triple integrals are usually used for calculation of volume. We define domain D to lie between z equal to gamma 1 of xy and z equal to gamma 2 of xy. Basically, if you are given an explicit function in xyz, you need to separate out the x and y part from the z part to get the limits of z. Now, this domain D is projected on the xy plane. That is, put z equal to 0 in the explicit function that you have been given, and solve for y in terms of x. So you will get some y equal to phi 1 x and y equal to phi 2 x. And if you put y equal to 0, then the limits which satisfy your function, that is the endpoints of your region, will be the values of x which we will find, that we can take these values to be a and b. So the volume of this region D will be as follows. We will express this as an iterated integral. This part will be integrated with respect to z first, then x first, then y, and then z. So the limits of z you can see are with respect to these two values of z that we had found earlier, gamma 1 and gamma 2, by separation of variables. Then for y, we found limits to be phi 1 and phi 2, and for x we know the limits are a and b. So let us take an example here. We need to find the volume enclosed by this region. So we know that this region is a sphere with center, origin, and radius 1. So separating z out, z from x and y, we'll see that z is plus minus root 1 minus x square minus y square. So these become the limits of z. That is this part and this part. F of xyz is equal to 1, so it will remain as it is. Then we take the projection of this domain along the xy plane by putting z0. So we get this over here, and like I said, you have to solve for y in terms of x. So y will be plus minus root 1 minus x square, and we get the limits of y. And then putting both y and z0, we get x square equal to 1. That is the limits of x at the endpoints. Like this is x equal to 1 and this is x equal to minus 1. So solving this integral, we'll get 4 pi by 3. Of course, it is very hard to solve this integral in Cartesian coordinates. And in the next lecture, we'll be seeing how to solve this integral easily using polar coordinates. Let us take an interesting example. We need to find the volume enclosed by these two curves, y square plus z square equal to r square and x square plus y square equal to r square. So we know in 2D that these two equations represent the equations of a circle. Now just imagine in 3D, if you have a circle, it will be extending from x going from minus infinity to infinity, and in this case z going from minus infinity to plus infinity. So that means that these two curves are actually cylinders, one along the x-axis and one along the z-axis respectively. Now to find the volume enclosed by these, we can see that since these two cylinders are symmetric about the x and z axis, it will subtend an equal volume in all 8 quadrants. So we just need to find the volume enclosed in one quadrant and then multiply it by 8 to get the total result. We will get somewhat of a weird figure, as we can see over here. So we just try to sketch it out and we'll get something like this. Now to find the volume of this, we know that we can find base into height and then integrate it throughout its entire height to find the volume of this part. So let us take this point over here and draw this cross section. So we can see that the cross section is a rectangle. So this height is y, and the distance of this point from the center line will be x. Also this part is y, and this part, the distance of this part from the center is r, and we know that this cylinder is x square plus y square equal to r square. So to find this distance using Pythagoras theorem, we can see that this is root r square minus y square, and from this equation we know that this is equal to x. So this rectangle is actually a square. So the area of this base is x square, and the area of this infinitesimal height is dy. So here volume of this part will be integral x square dy going and y going from 0 to r. And we know that x square can be written from this function as r square minus y square. So we will get an integral in one variable going from 0 to r, and this integrated gives us the volume 2r cubed by 3, and so the total volume enclosed is 8 into this, which is 16r cubed by 3. So thank you for watching this lecture. You can scan this QR code to know more about us. So see you all in the next lecture.